Today we will begin a new chapter titled Pair of Linear Equations in Two Variables. You will recall that the following are the examples of linear equations in two variables: 2x plus 3y is equal to 5, or x minus 2y minus 3 is equal to 0. You have also studied that a solution of such an equation is a pair of values, one for x and the other for y. That is, if you put those values of x and y in the equation, the two sides of the equation will be equal. For example, in equation 1 above, if you put values of x and y as x is equal to 1 and y is equal to 1, then the LHS of the equation will be 2 into 1, because x is equal to 1, plus 3 into 1, that is equal to 2 plus 3, that is equal to 5, which is equal to RHS. Therefore, x is equal to 1 and y is equal to 1 is a solution of the equation 2x plus 3y is equal to 5. Now let us substitute x is equal to 1 and y is equal to 7 in that same equation. Then the LHS will be 2 into 1 plus 3 into 7, that is equal to 23, which is not equal to the RHS. Therefore, x is equal to 1 and y is equal to 7 is not a solution to the equation. Geometrically, what does this mean? It means that the point 1, 1 lies on the line representing the equation 2x plus 3y is equal to 5, and the point 1, 7 doesn't lie on that line. So every solution of the above equation is a point on the line which represents that equation. Now consider following two equations which represent certain conditions. Y is equal to half x, equation 1, and 3x plus 4y is equal to 20, equation 2. These two linear equations are in the same two variables x and y. Equations like these are called a pair of linear equations in two variables. Algebraically, the most general form of a pair of linear equations is a1x plus b1y plus c1 is equal to 0. This is the first equation. And a2x plus b2y plus c2 is equal to 0, the second equation, where a1, a2, b1, b2, c1 and c2 are real numbers such that a1 square plus b1 square is not equal to 0 and a2 square plus b2 square is not equal to 0. That means a1 and b1 both cannot be 0. Similarly, a2 and b2 both cannot be 0. Now let us see some examples of the pair of linear equations in two variables. Like 2x plus 3y minus 7 is equal to 0 and 9x minus 2y plus 8 is equal to 0. Then 5x is equal to y and minus 7x plus 2y plus 3 is equal to 0. Then x plus y is equal to 7 and 17 is equal to y. So these are some of the examples of pair of linear equations. You have also studied previously that a linear equation in two variables is geometrically or graphically represented by a straight line. Hence, a pair of linear equations in two variables are represented by two straight lines. Consider together. You have studied in class 9 that given two lines in a plane, only one of the following three possibilities can happen. Possibility number one is that two lines will intersect at one point, as shown here, or the two lines will not intersect, that is, they are parallel, as shown in this figure, or the two lines will be coincident, that is, the two lines will coincide. Now let us understand the above three situations by graphical representation of the pair of lines. Now example 1, represent the following pair of linear equations graphically. Now we have been given these two equations, x minus 2y is equal to 0 and 3x plus 4y is equal to 20. Now we know that a linear equation is represented by a straight line. And to draw a line, we need at least 2 points, that is two solutions. That means we have to find out two solutions of each of these equations. Now here equation number 1, y is equal to x upon 2. So we can have 2 points. When x is equal to 0, y will be equal to 0. And when x will be equal to 2, y will be equal to 1. So we have 2 points 0, 0 and 2, 1. Now let us plot those points. First point is 0, 0, that is A. And second point is B, which is 2, 1. Now we can draw a line through these 2 points. And this line represents the equation x minus 2y is equal to 0. Similarly, we find the two solutions of the second equation and we draw the second line. And now we find that these two lines intersect at point Q, whose coordinates are 4 and 2. So, if the lines intersect at a point, then that point gives the unique solution of the two equations. That means this particular point will satisfy both the equations. In this case, the pair of equations is said to be consistent. Example 2, represent the following pair of linear equations graphically. Again, we have been given two equations, x plus 2y minus 4 is equal to 0, 2x plus 4y minus 12 is equal to 0. Again, uh, we have to follow the same procedure as in example 1, and we have to find two solutions of each equation and then draw the lines. So if we draw the lines, we can see that there are these two lines, that is one line representing x plus 2y minus 4 is equal to 0, that is first equation, and the second line representing the second equation. We find that these two lines are parallel, that is they will never intersect. So if the lines are parallel, then the pair of equations has no solution. So in this case, the pair of equations is said to be inconsistent. Now example 3, again we have been given these two equations, a pair of linear equations, and we have to find the solution. So again, following the same procedures as before, we can draw two lines on the graph. One line is representing the first linear equation, that is 2x plus 3y is equal to 9, and the second line represents linear equation 4x plus 6y is equal to 18. Now we can easily notice that these two lines are coinciding. So if the lines coincide, then there are indefinitely many solutions, each point on this line being a solution of these two linear equations. So in this case, the pair of equations is dependent and consistent. So if the two lines represented by the equations a1x plus b1y plus c1 is equal to 0 and a2x plus b2y plus c2 is equal to 0 are intersecting, then you will find that a1 upon a2 will not be equal to b1 upon b2. If the lines are coincident, then a1 upon a2 will be equal to b1 upon b2, and that also will be equal to c1 upon c2. That is, all the three ratios will be same. And if the two lines are parallel, then a1 upon a2 will be equal to b1 upon b2, but not equal to c1 upon c2. And the converse is also true for any pair of lines. Let us understand this by one example. On comparing the lines a1 upon a2, on comparing the ratios a1 upon a2, b1 upon b2 and c1 upon c2, find out whether the lines representing the following pairs of linear equations intersect at a point, or whether they are parallel, or whether they are coincident. Now this is the first pair and this is the second pair. Now let us check the first pair. Now here a1 upon a2 will be equal to 5 upon 7, and b1 upon b2 is minus 4 upon 6. So here we see that a1 upon a2 is not equal to b1 upon b2. Therefore, these two lines intersect at a point. So they have a unique solution. Now let us take the second pair of linear equations. Now a1 upon a2 will be equal to 9 upon 18, which is 1 upon 2. Similarly, b1 upon b2 is equal to 3 upon 6, which is again 1 upon 2. And c1 upon c2, which is 12 upon 24, which is also equal to 1 upon 2. Now here we notice that all these ratios are same. a1 upon a2 is equal to b1 upon b2 is equal to c1 upon c2. Therefore, the lines are coincident. Now, so far we have discussed how to solve a pair of linear equations graphically. The graphical method is not always convenient in cases, particularly when the point representing the solution of the linear equations has non-integral coordinates like minus 1.753, 3.3, or root 3, 2 root 7, or 4 upon 13, 1 upon 19. So if the points have these kind of coordinates, then there is every possibility of making mistakes while reading such coordinates. So is there any alternative method of finding the solution? The answer is yes. There are several algebraic methods. We will discuss those methods in the next class. Thank you.